Every day, most of us use a piece of technology that could be key to treating and curing disease, developing new drugs, and maybe saving a lot of lives. You might carry it around with you in your backpack or a handbag. It might be in your car. You might keep it on your desk at work. Now, it's not a computer. It's not your smartphone. It's hand sanitizer. Now, you might be thinking about how in the late 1800s, when physicians started sanitizing their hands with antiseptics between treating patients, mortality rates in hospitals plummeted. Well, that's not what I have in mind. Hand sanitizer is not going to transform global health in that capacity any further. So why do I say hand sanitizer could lead to breakthroughs in medicine and maybe save a lot of lives? It's because hand sanitizer has inspired the development of a new 3D bioprinting technology that gives researchers practically unlimited freedom to perform experiments in ways that are otherwise impossible. I believe this new freedom will unleash the creativity and productivity of researchers as they develop and test new therapies and study the fundamentals of tissue malfunction. Now, if you don't know much about 3D bioprinting, or 3D printing more generally, think of it like this. To create a 3D structure of my own design, I need to take a liquid and push it through a translating nozzle. And that liquid has to stay right where I put it until it turns into a solid. And by laying down layer after layer of liquid that rapidly turns into solid, I build up a 3D structure. This simple picture captures most of 3D printing out there, where the liquid that turns into a solid is just melted plastic that rapidly cools and solidifies. So what's 3D bioprinting? I mean, you can't just melt living tissue and push it through a nozzle. Well, 3D bioprinting, the liquid I push through the nozzle is a mixture of living cells and all the materials they need to live. And the problem is that this liquid doesn't rapidly solidify and hold its shape like melted plastic. And this is where hand sanitizer comes in. To understand how hand sanitizer solves this problem, let's think about what makes hand sanitizer unique. Imagine walking down the aisles of the grocery store or the pharmacy and seeing all the personal care products lining the shelves: shampoo, conditioner, lotion, body wash, liquid soap, and hand sanitizer. What's different about how hand sanitizer looks? If you haven't thought of it yet, the answer I'm looking for is bubbles. You never see bubbles trapped in bottles of all those other products, but you always see bubbles trapped in bottles of hand sanitizer. Those bubbles teach us that hand sanitizer has unique physical properties that those other products lack. Those bubbles are the key to turning hand sanitizer into a tool for biomedical research. Now, there's an entire field of physics devoted to studying materials like hand sanitizer. Formerly, it's called soft matter physics. Those of us in the field sometimes call it squishy physics. And in the world of squishy physics, decades of research and debate has gone into understanding materials like hand sanitizer. We ask simple questions like, are they solids? Are they slowly flowing fluids? Maybe they're really soft glasses. And what gives them their properties? It's answers to questions like these that teach us why we always see bubbles trapped in bottles of hand sanitizer, but never in those other soft, squishy materials. In all, solids, liquids, and the soft, squishy stuff in between, buoyancy forces drive bubbles up. You know this. Bubbles rise in water. Bubbles even rise in really viscous fluids like molasses. And I hope this picture of molasses here reminds you, you never see bubbles trapped in jars of molasses. So if bubbles rise in water and molasses, but they don't rise in hand sanitizer, the hand sanitizer itself must be resisting the force, holding the bubble still. Materials that can resist forces while sitting still are solids. Think about it. You push on a fluid, it flows. You push on a solid, it deflects or bends a little bit. But it comes to rest and resists the force, sitting still. Bubbles in hand sanitizer are at rest, sitting still, resisted by the hand sanitizer. Hand sanitizer must be a solid. But I can pour hand sanitizer. I can pump it up through a nozzle. I can smear it all over my hands. That seems like a fluid. Well, that's right. Hand sanitizer is a fluid when it's flowing. Both perspectives are correct. Hand sanitizer is a solid when sitting still and a fluid when flowing. Now, to understand how that works and to convince yourself it's true, let's think of another material that's a solid when sitting still and a fluid when flowing. It's the ball pit kids play in. When kids lay still in a ball pit, the ball pit can support their weight, acting like a solid. But when kids start stroking their arms and kicking their legs, they can literally swim. When flowing, the ball pit acts like a fluid. Hand sanitizer is just a microscopic version of that ball pit. In fact, hand sanitizer is made from tiny little microscopic balls, all packed together. The only difference is those little balls are soft and squishy and swell up in water-based liquids. So now you know how hand sanitizer works. How do we turn it into a tool for biomedical research? Well, here's the idea. If I can randomly disperse bubbles throughout a bottle of hand sanitizer, what if I place them at carefully chosen locations in 3D space to create a structure? I'd be 3D printing with air. And if I can randomly place kids anywhere in a ball pit, what if I placed those kids at carefully chosen locations in 3D space to create a structure? I'd be 3D printing with kids. If I can 3D print with air into hand sanitizer or kids with a ball pit, why can't I do the same thing with living cells? I just have to develop a material that has the physical properties of hand sanitizer, but all the chemical properties of the liquids we typically grow cells in. So that's what we did. For the past 5 years, my lab at the University of Florida has been developing a cell culture medium that has the physical properties of hand sanitizer. Here you can see what it looks like to 3D print into this material. We can create 3D structures of high complexity out of nothing but liquid, trapped in space, just like bubbles in the hand sanitizer, just like kids in the ball pit. With this method, we can 3D print precise, complex structures out of living cells. Just look at these tiny Matryoshka dolls nested inside one another. The smallest one is about the size of a grain of rice. Now, with these tools, we've conducted a lot of different investigations. Here you see microscopic examples of our 3D printing method at work. We've developed tiny models of the human liver to test compounds for toxicity. We studied how precisely fabricated cellular structures evolve in shape under the forces cells generate. We've created models of developing tissue, hoping one day to use our tools to understand critical aspects of embryonic development. In one of our investigations, we 3D printed model brain tumors surrounded by immune cells. The idea was inspired by our colleagues in the Department of Neurosurgery, Drs. Catherine Flores and Dwayne Mitchell. A few years ago, they developed a new type of immunotherapy effective against brain tumors. They were targeting a type of brain cancer called glioblastoma. Now, some cancers aren't susceptible to the revolutionary new immunotherapies that have been developed recently, and glioblastoma is one of them. By infecting mice with glioblastoma and testing hypothesis after hypothesis, they eventually came up with an effective immunotherapeutic strategy. The process took years. Now imagine if they could have placed the cells anywhere they wanted in the mouse and seen directly into the mouse's brain at high magnification and watched precisely as the immune cells attacked the tumor and rapidly tested their hypotheses and harvested the cells whenever they wanted to for biochemical testing. In other words, imagine if they could do experiments that replicate what happens in the mouse without all the restrictions of working with mice. Their discovery could have been made in a matter of weeks or months, not years. Teaming up with them, our labs proved that this fantasy may soon be reality. My PhD student, Cameron Morley, 3D printed hundreds of glioblastoma tumor models surrounded by immune cells, varying things like their proximity to the tumor, and testing all of the necessary controls and replicates. He performed time-lapse imaging on a microscope at high resolution, watching in detail how the immune cells attack the tumor with a level of precision you just can't get when working with a mouse. To test whether the cells in our hand sanitizer material behave the way they do in a mouse, Cameron used our printer to harvest the cells. You can see that by embedding cells in a material like hand sanitizer, we're able to suck the immune cells out and harvest the tumors. In fact, this process is a lot like pumping material up through a hand sanitizer dispenser, except in our case, the needle, the dispenser tube is a fine needle about as narrow as a human hair, precisely positioned by a 3D printer, sitting on top of a microscope. We're able to move this needle around, sucking out all the immune cells, and then come back and suck out the tumor. Cameron harvested the cells from his hundreds of different experiments, handed them off to Catherine Flores' lab for biochemical analysis. And based on their gene expression profiles, we found that cells in the hand sanitizer material indeed behave the way they do in the mouse. Now, this first investigation of glioblastoma was a critical first step to convincing the world and convincing ourselves that this crazy idea of turning hand sanitizer into a tool for biomedical research would enable us to perform experiments that reproduced what happens in living tissue, but without all the restrictions of working with real live animals. We hope with enough examples like these, we can convince the whole world to use our technology. Now, most of the biomedical research world out there recognizes the critical importance of studying cells in 3D contexts. It's the first step toward mimicking the body. But they also realize that it's usually not worth the time, effort, and expense to create 3D structures out of living cells. It's really hard to do. I think we've made it a lot easier to do. Taking inspiration from the bubbles in hand sanitizer, developing a new 3D bioprinting technology combined with a 3D culture medium. Today, we're 3D printing the experiments we imagine, rapidly testing our hypotheses, and soon, I hope, accelerating the pace of life-saving discoveries in biomedical research.